Marcel here, and welcome to another video. This one will be about the Burnside problem, which is a problem in group theory. So I will sort of assume that you've seen groups before, but if you haven't or not too much, well, if you haven't at all, then this is going to be probably really difficult and incomprehensible. But if you've seen like even a little bit of groups in your math courses, you should be fine to follow along this video. We're just talking about sort of orders of elements, and usually you know the group axioms, but not too many other facts besides those. Okay, so let's just get started. So the Burnside problem started with, of course, someone named Burnside. So William Burnside. This is not the Burnside. If you've ever been to McGill University, there's a building called Burnside Hall, and that's where the math department lives. But these Burnsides are not related. In fact, the one at McGill is not named after a person at all. It's just named after the fact that it's beside a hill, and the hill is Mount Royal in Montreal. Anyway, I'm digressing. Probably not interesting at all unless you're from Montreal. Okay, so William Burnside asked in 1902, can a group be infinite while every element in it is finite? In fact, he said it in some more old-timey speak. But anyway, so yeah, so he asked, can a group be infinite while every element in it is finite? And this is called the general Burnside problem. And this is not exactly what we're gonna study here. Okay, it was solved in 1964. 1964 by Golod and Shafarevich. Okay, and I just want to talk about it because, I mean, this is what he asked. It's an interesting question in and of itself, and very similar to what we're going to do in this video. And anyway, what did Golod and Shafarevich show? They showed that the answer is true. So they found an infinite, finitely generated group, and all of the elements have finite order in this group. Okay, but anyway, that's not what we're going to quite show. We're going to show something subtly different. We're going to ask, can a group, so the question, can a group be infinite if the order of every element is bounded by some fixed integer n? So it's subtly different because in the top, we just wanted every element to have finite order, which means eventually you take it to some power, it'll get to the identity. But of course, you could have elements of arbitrarily large order. This question says, can a group be infinite if the order of every element is bounded by n? So there is some n such that for all elements in this group, say G, we have the order of the element is less than n. Okay, and I'm not going to spoil the answer. We do have an answer. This question is solved, but I'm going to keep you on your toes, and well, you could skip to the very end of the video if you just wanted to know. But we're gonna like work up to the answer. We're gonna show some small examples for small n. Okay, so we're gonna define the Burnside group, and we're gonna study. This is the group we're gonna study. So definition: the free Burnside group with generators of order n. Oh, sorry, with R generators of order n. There's a parameter R in there, denoted BRN. You should remember that R comes before N in this. It's a little bit confusing, but you can remember that by thinking like it spells a burn side. Okay. is the group with R generators. Yeah, I mean, I said that twice, but that's because this is the thing we're defining. Of order n, okay. The R generators x1 through xr, such that for all s in B Rn, s to the n equals e. And e is, of course, the identity. And it's a multiplicative group. That's why we use the powers like that. We denote the powers like that. So Brn is actually the free group. The free group is just if you have all these R generators and you take any combinations of them. Of course, inverses cancel each other out and stuff like that. Okay, and so it's the free group, but we mod out by the condition that s to the n should be equal to e. So this is s in Fr. Okay, so that's the free Burnside group with R generators of order n. Okay, and the Burnside problem. So of course, yeah, this is the free Burnside group. But hang on, what did I say? What did I have? I remember there was a note about this. I forgot to write it down in my paper notes. Oh yeah, okay. So the general Burnside problem, not the general Burnside problem. That's an actual thing. This Burnside problem Q here, okay, isn't about the free Burnside group. It's technically about any group with the order fixed by n. But if the order has R generators, and order n, like a maximum order n, then you can map the free Burnside group to this, to your group. So really, we've boiled down the question to studying Brn. Okay, that's a little note there. So anyway, this is what we're going to study, and we just want to know, is this finite for all R and all n? Okay, so we're going to just work our way up. So the map of this video is we're going to do n equals 2, n equals 3, then n equals 4. And then there's one more n that's solved, which is 6. And then we'll talk about bigger n later. Okay. Actually, 6 we're not going to talk about, sorry. 6 is we're not gonna have time for 6 in this video. But we'll mention 2, 3, and 4. We're gonna prove. Okay, so n equals 2. All right, n equals 2 is very easy. And so we can just jump right into the theorem. This is proved by Burnside himself in 1902. And the theorem is the order, by the way, of a group is the size, a finite group. Yeah, it's the size, and the order of an element is the power to which you take that element and you get 1, the smallest power. Okay, I'm sure you know that already. I'm just saying it. The order of B R2 is 2 to the R. Okay, so it's finite, of course, and that's its order. So proof, for every S and T in BR2, we have S squared equals T squared equals ST squared equals E, right? Because every element has order 2, by assumption. Then since ST equals E, which is just ST squared, we can multiply on the left by S and on the right by T, okay, to get, so S, ST, ST, and then T, and on the right you get, well, you multiply E by the same thing, so you get ST, but of course S squared is equal to E, so let's just do it in red. We cancel out this S squared, and we cancel out the T squared as well. Sorry, that's really messy. And you get T as equals ST. Okay, so since S and T were arbitrary, so BR2 is abelian with R generators, each of order 2, and so EBR2 is isomorphic to Z mod 2Z R, which has order to the R. Okay, so that's the proof of that. It's really easy. Okay, now that's okay. What else? What else did Burnside show? So Burnside also showed the 2, 3 is equal to 27, and B 2, 4 is equal to, or is less than equal to 2 to the 12. Okay, and then he also showed. Now we're going to go to n equals 3. Okay, he also showed, also Burnside. He also showed that BR3 is finite. So by the way, I mean, these are special cases, and I already said we're going to do n equals 3 and n equals 4 further in the video. So these are just preliminary examples that Burnside showed, but we're going to, I mean, we're going sort of chronologically, and we're going to be able to prove n equals 3 and n equals 4 in full generality. Just if you sit tight. Okay, so Burnside also showed that BR3 is finite. He did do that, and he used a pretty convoluted method that we're not going to show. He showed that its order is less than equal to 3 to the 2 to the R and minus 1. That's in the exponent. Okay, so the argument's like 2.5 pages or something. So we're not going to do that. We are going to show that theorem for R greater than or equal to 1, BR3 is less than or equal to 3 to the MR, where MR is less than or equal to 3 to the R minus 1. So yeah, so 3 to the R minus 1 is definitely greater than 2 to the R minus 1. But, you know, it's easier, and it still shows that it's fine. So we're going to do that. Where did I find this argument? I found it in this book called The Theory of Groups by Marshall Hall Jr. There you go. I don't know. The Theory of Groups, and it's on page 320 if you can book. If you don't have the book, you could, I don't know, find it. I'm sure you could get a great pirated version somewhere. I'm sure you could. I don't know where exactly, but anyway. So let's just prove this. So proof. So this is going to be a bit of a longer argument. So because every non-identity element in BR3 has order 3. The group is a 3 group. Okay, and thus has order 3 to the like the order a power of 3. Okay, so that kind of shows that sorry, this is actually equals. Okay, that shows that it's equal to 3 to the MR for some MR. Okay, now we're gonna do the induction on R. So when R equals 1, that's one generator. It has order 3, so BR3 is isomorphic to ZR3Z. Okay, which is obviously finite, and you have M1 is equal to, well, 3 to the 1, right? So M1 is 1, which is of course less than or equal to 3 to the R minus 1 here is 0. In fact, it's equal. Okay, so that's the base case. So now that we've proven this base case, we just want to show that MR plus 1 is less than or equal to 3 times MR. Okay, and we would show the general case. So now suppose that bk3 is less than equal to, or sorry, is equal to, I keep putting less than equal to, is equal to 3 to the mk for some some mk less than equal to 3 to the k minus 1. That's the induction hypothesis. Okay, and so we have st to the 3 equals e, right? So tst is equal to s inverse t inverse s inverse. That's just by taking this thing expanded out, st, and then doing some inverses. And this is for all st in the group, in b, k plus 1, 3. Okay? So, well, yeah, this is both. Okay, so now we form bk plus 1, 3 by adding a generator. It's going to be a new generator, g to bk3. So bk3 already had k generators, and we're adding a new generator. Okay, so s in bk plus 1, 3. Okay, you can write s as s is going to be equal to s1 g plus or minus 1, s2 g plus or minus 1, g plus or minus 1, all the way to h. Okay, it doesn't really matter. I mean, h is a priori, h could be large. The point is that, you know, s can be written as a product of generators, and g is one of the generators, right? And the other generators are all in the original group, bk3. So where si is in bk3. So we combine, the point is we combine all the other generators to form some si in bk3, and only the g's are left, but they're possibly g inverse. G's are possibly inverse. Okay? Now, if in the product any of the g's that are adjacent have the same sign, then we can replace, right? Because we have this tst is equal to s inverse t inverse s inverse. So what can we do with that? Well, you can see that g sig is equal to s I inverse g inverse si inverse, and then the same thing for g inverse sig inverse. That's just si inverse g si inverse. Okay, and so we would then be able to reduce the number of g's by 1. Right? So note that there are 2 g's here. I'll circle them. There's 2 g's, and there's only 1 g here. So if the 2 adjacent g's have the same exponent, we can reduce the number of total like g's in the expression by 1. Okay, same on this side, right? 2 g's on this side, and there's only 1 g on that side. Okay. So now we reduce all of them to the case where they alternate in sign, because this is if they have the same sign side by side. We repeat this process until the g's are all alternating in sign. Okay, so reduce, so repeat until the g plus or minus 1s alternate in sign. Okay, but then there's, you know, but we can still do, I mean, the surgery isn't over. Okay, because we can keep going. Okay, since g cubed is equal to e, okay, g inverse is equal to g squared. Okay, so now I'm gonna need more space for this. Let's start a new page. this part gets like super kind of algebraic, so just bear with me here. So we're gonna write S equals S1 all the way to Si, G Si plus 1, G inverse, Si plus 2, G all the way to Sn, right? So this is, they alternate in sign now. So since this G inverse is actually G squared, okay, we can say this is equal to S1, Si, G, G Si plus 1, G, and then G Si plus 2, G Sn. So we've just changed G inverse to G squared here. Okay, and I've kind of like put spaces to organize everything. But now that's interesting because we can change S1 to so we can change this to Si. So G Si plus 1 G by what we had before. Remember this rule, the TST is S inverse T inverse S inverse. This becomes Si plus 1 inverse G inverse Si plus 1 inverse. And then, is that right? G inverse, yeah, I'm getting a little lost here in the, in what I have. Yeah, so, oh yeah, amazing, okay. And then Si, same thing here, right? So Si plus 2, G inverse, Si plus 2 inverse, and then you continue, okay? But now, we've reduced the number of G's by 1. Let's count. So we had, in the beginning, we had 3 G's, and now, well, we made 4, just temporarily, we made 4 of them, and then we reduced it so there's a G here and a G here. And in fact, they became both G inverse, so we can do the previous step again, where we reduce it even more. So it just keeps reducing. Okay? So we have thus. And of course, these are in S, right? Or sorry, these are in the BK3. So there's some other, you multiply the S's and you get different SI's, but that's fine. Okay, so we have reduce the number of G ones by 1. We can do the same if instead it was G inverse G G inverse. Like here it was G inverse G, but we could do the same thing. I don't want to repeat it. And also we have two adjacent products again, or 2 adjacent G's with the same exponent, so we can do the previous step again. And so by repeatedly doing this, we find that there are at most, oh my god, that at was really high. So at most 2 G's in the expression. Okay, but we're not done. There's, we can do, if you thought we were done, no, we're not. We can do a further refinement because G is equal to G inverse, right? Because you start with G3 equals E and then you do the inverse twice. So S G inverse S2, S1 G inverse S2 G S3 is equal to S1 G inverse S2 G inverse S3. Okay, and now we see again 2 things side by side, sort of straddling something in the middle. So you get S1 S2 inverse G S2 inverse, then G inverse, and S3. And so this is a new S, right? So equals S1 prime, G S2 prime, G inverse, S3. So not only can we find that, can we sort of insist that there are at most 2G inverses, so at most 2 G's in the expression. If there are two, we can insist that the positive exponent comes first, and the negative exponent. So here we have negative, then positive, and we can switch it around. Okay, so now we're almost done. So any S in B k plus 1, 3 is of one of the following forms. So yeah, there are at most 2 G's, so there could be no G's. So S could be just S1, or it could be S1G S2, or it could be S1G inverse S2, or else it could be S1G S2 G inverse S3. And of course, we just showed that we can't have the inverse first. So that's it. There are 4 possibilities. And of course, so S1, S2, S3, if they're there, would be in B, K, 3. Okay, then the previous group. Okay, so there are 3 to the MK possibilities for the first case. That's by the induction hypothesis. Then there are 3 to the 2 MK possibilities for the second case. The same thing. So actually, the same thing for the third case, right? So S1, S2, S1, S2. And then 3 to the 3 MK for the fourth case. Okay, so all in all, there are 3 to the MK plus 2 times 3 to the 2 MK plus 2 times 3, sorry, there's not 2 times here, it's only 3 to the 3 MK elements, at most elements in B K plus 1. So K plus 1, comma 3. But now let's just make a strict upper bound. There's 3. So this is less than 3 to the 3 MK. This is 2 times 3 to the 2 MK. So actually, well, it's less than 3 times that. So if we change this 2 to the 3, it'd be less than that still, and then that would be a 2K MK plus 1, right? But MK, remember, okay, so there's kind of an assumption here. MK is going to be at least 1, right? We already showed above that MK equals 1 when the group is cyclic. So it's at least 1. So 3MK is at least 2MK plus 1. So I just want to write this. Okay. So this is definitely strict. So this is where the inequality is strict. The inequality is not strict, but it's still a less than equal. And then this will just keep the same, 3MK. Yeah, the strictness comes from the first term. Okay. And so this is equal to 3 3MK plus 1. But if it's strictly less than this, and it has to be a power of 3, because the very first line, yeah, right, the group has order a power of 3, we find that the order of B K plus 1, 3 is at most 3 to 3 MK. Okay. And of course, so there we go, right? So because we already showed above here that, where is it? What was the induction hypothesis? Induction hypothesis was that mk is less than or equal to 3 to k minus 1. So you times it by 3, and then you add 1, and so it becomes, you add 1 in the exponent, sorry. And so mr is less than or equal to 3 to the r minus 1 for all r. That's really what we've shown down here. Okay? Yeah, I mean, sorry, I was a little weird about this, but really what we're trying to say is that mk plus 1 is at most 3 times mk. And that's the induction step. So, yeah, so mk plus 1 is less than or equal to 3 mk, really. Okay, I'm sure you got it. I'm just being slightly confused. All right, so we have shown that Burnside groups of exponent 3 are finite. All right, so actually, let's just make a little comment. In fact, we've, in 1940, Levi and van der Waerden showed that MR is actually equal to R choose 3 plus R choose 2 plus R. Okay, so that settles exponent 3. All right, so now we're gonna do exponent 4. So I just want to comment the exact order. So now we're going n equals 4. Okay, the exact order of BR4 is known only for R less than or equal to 5. Okay, maybe it's been updated now, but anyway, we don't know BR4 as well as we know BR3 or BR2 or BR1. Actually, I mean BR1 is the identity. Okay, so but we can still show that BR4 is finite for all R. Okay, and that's what we're gonna do in this part. So first we're gonna prove a lemma. There's 2 M's there, and all the kind of gross steps are gonna be in this lemma. But it's interesting that, you know, you'd expect that 3 was a lot harder than 2. 4 is not a lot harder than 3. It's really actually like a similar difficulty. Okay. So here's the lemma. Let G, that's capital G, I wrote little g, be a finite group of size big N. Okay, all of whose elements have order dividing 4. So they either have order 1, 2, or 4. Okay, then if we join to G, new generator, G not in G, such that G squared is in G, then letting G prime equal G union G mod out by S to the N. I guess I'll write it like that. You know what I mean? You just make, sorry, not S to the N, S to the 4. You make powers, 4th powers equal the identity. So this group G prime, obtained by adjoining G and then making 4th powers equal to the identity, is finite. Okay, so this is where, you know, really most of the work is going to be in this lemma. Then later, after this lemma is proved, it's really easy to show from here that BR4 is finite. So here's the proof of the lemma. Okay, so we have G inverse equals G cubed because G to the 4 is equal to E. And of course, GS to the 4 is equal to E for all S in G prime. So GSG is equal to, sorry, not that. G, S inverse, G inverse, S inverse, G inverse, S inverse, right? By just taking, there's, GS, 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 and then doing 5 inverses. But this is equal to S inverse G, then G, yeah, so this is a G. Sorry, my G's and my S's look very similar. It's a fault of my elementary schooling. Okay, so G inverse is G cubed, so G squared S inverse G squared G S inverse, okay? Yep, so we just changed all the G inverses to G cubes. All right, now so since G squared is in G, we can rewrite this GSG equals S inverse G S prime G S inverse. Okay, so we're setting this to be S prime, and of course S prime is in G. All right, so from S in G, oh sorry, not from, this is fix. So fix an S in G. Fix an S in G, and we write, again, the proof is going to start the same. So we write S equals S1 G, S2 G, all the way to G, Sn. And this time, so remember, it could be G or G inverse the other time. It could be G or G inverse last time, but now we can change all the G inverses to G, because G inverse is equal to G squared. So this G squared is in G, right? So it can just kind of get like sucked into the S. Like if this was G inverse, okay, it's actually the same as that, but then this is in G. Okay, so we can just change S2. So that's why it's like almost it's almost easier in this case. We don't have to worry about all the little funny exponents. We always have G. Okay, the exponent's always 1. Where SI is in G, all I. Okay, so we will say this word has length n. Okay, and n is here. Okay, I'm using the letter n. N is, we had n before, but I'm gonna use the word the variable n for the length here, because we're fixing the exponent to be 4. So this word has length n. Of course, it doesn't have length n, right? Like there's g's everywhere, but the point is there are n elements of the original group big G, and so we're gonna say this word has length n. Okay. Now if we apply this rule, so apply star. Okay. Sorry, I need a new page. Apply star, we get S equals S1G, okay, G, S I minus 1, S I inverse, G S I prime, G S I inverse, S I plus 1, G, and then, G S N. So what have we done? We've taken some GSIG, like a triple GSIG, and we've made this, kind of gnarly expansion of it, where there's now a new SI prime and SI inverses get tacked on before. But if you notice, there were 2 G's here and there are 2 G's here. So the word has not increased in length. By length, I still mean this thing, right? So the same number of G's up here and the same on the left as on the right. So we applied star. We didn't change the length of the word, but we have new coefficients, sort of SI, new sort of subwords in here. Okay, so note that SI minus 1 has been replaced by Si minus 1 Si inverse. Okay, so if some Si is E, then two neighboring G terms, or I guess factors, combine, and the length decreases. In fact, it decreases by at least 1 or 2 or 3. I mean, it doesn't matter. So if Si prime, for example, was E, then G and G combine, because G squared is E. G squared is in S. And so this whole thing would be in S. And so the length actually decreases by 2. Anyway, it doesn't matter what it decreases by, but it decreases strictly. Okay, so here's the strategy, okay? So strategy. Repeatedly apply this. Let's call it double star. Repeatedly apply double star to hopefully reduce the word length. Okay, so we're gonna try and prove that the word length must decrease. Well, we'll see. There'll be a condition for the length to decrease. Okay, so now note that in double star, So note that, in double star we replace Si minus 1 by Si minus 1 Si inverse. So we could replace, note that we can replace S2 by S2 S3 inverse. Okay, and then we can replace this guy by I guess, like, what am I trying to say? We can replace S2 by, I'm getting a little messy here. Si minus 1 has been replaced by this. We can replace Si minus 2. Okay, I'm sorry, I don't want to, I kind of mess up the notes here. We can replace Si minus 2 by Si minus 2, Si minus 1, Si inverse. Because we replace Si minus 1 by this. So now Si minus 2 we can replace by Si minus 2 times this thing, which was already replaced, inverse. And of course this is equal to Si minus 2, Si minus 1 inverse. I'm just taking the inverse here. Right. So we see that we can replace. So now I'm gonna move this down here. I wish I knew how to move. Okay, so this goes up here. So note that we can replace S2 by S2 S3 inverse, or S2 S4 S3 inverse, or S2 S4 S5 inverse, S3 inverse, and so on. Okay. Right, this is Si minus 2, Si minus 1, and then if we wanted to do Si minus 3, it would be the same thing, but it'd be Si minus 3, then Si minus 1, then Si minus 2. The pattern is, so here's the pattern. When I is even, Si appears to the left of Si minus 1 inverse, and when I is odd, Si appears to the right. Si inverse appears to the right of Si minus 1. Okay, so let's just take a moment and stare. So S3 it appears as an inverse and it appears to the right. Then S4 doesn't appear inverted and it appears to the left of S3. Then S5 appears inverted because it's odd to the right of S4, and so on. Okay. Okay, so if any one of the products is the identity, we reduce the length of the word, right? So now we have a new, so our strategy is to replace S2 by a bunch of things and hope that one of them is the identity. Okay? To do that, we need the length of the word to be long enough. So suppose n is greater than or equal to m plus 2. Then, in like, why plus 2? Because S2, we can repeat this thing. Like when I say etc. here, there's n minus 2 possibilities, right? Eventually we're going to run out of things. We need I minus 2 to equal S2, so we need I to be, and I is at most n. Okay, so then in the list of possible replacements for S2, either E appears, or if E doesn't appear, then because the group only has m elements, so either E appears or some element is repeated. Okay. So what I'm trying to say is, if n is greater than m plus 2, there are m different replacements for S2. So if E appears, we're done. We reduce the length of the word. If not, then we have two possible replacements are actually equal to each other. In other words, so one case, so since if two of the replacements are equal to one another, it looks like this: S2 all the way to S2J, S2J plus 1 inverse, S3 inverse. That's what one of them looks like. And the other one looks like this. It looks like S2, S2K, S2K plus or minus 1. Right? We don't know whether this is smaller or bigger, but it's odd. S3, and the reason I say one case is because we don't know whether this one's bigger or not. Okay, but it's okay. We'll do this case first. But if these two are equal, then you just get rid of all the S2s on both sides and the S3s, like the even ones on the left and the odd ones on the right. We get S2J plus 2 all the way to S2K, S2K plus or minus 1, S2J plus 3 minus 1 is equal to E. Okay? So it is possible to apply double star to S2J plus 2 instead. Oh my god, what happened? Is the recording still going? How did this happen? Sorry, my luckily the whole computer didn't crash, but the program crashed. Anyway, it saved my file. So what was I saying? So this element here equals E. All right, so we abandon our strategy of looking at S2. Why don't we look at S2J plus 2 instead? So we apply double star to S2J plus 2 instead. And we can reduce the length of the word. Okay, so that's what happens in the one case, and in the other case, I'm not going to redo the whole thing. But if instead we had S2, S2j, S2j minus 1, inverse, S3 inverse. So instead of plus 1, we had minus 1. The same thing, we find we can apply double star to S2j plus 1 instead of S2j plus 2, and find a word whose product is E, like a replacement whose product that's actually equal to E. Okay, so any word of length n greater than or equal to 2, n greater than or equal to m plus 2 can be reduced. Okay. Hence, any s in G prime can be represented by a word of length less than or equal to m plus 1, and a word of length less than or equal to m plus 1. How many possibilities are there? And there are less than or equal to m to the power of m plus 1, right? Because in a word of length m plus 1, there's all the SIs, there's m plus 1 SIs. And how many choices do we have for each SI? We have m, so it's m to the power of m plus 1 possibilities for s. And so, this is a huge number, but we conclude, so G prime is finite. Okay, so we have shown that, what did we show? Let's see the lemma again. So G is a finite group of some size, m, and the elements all have order dividing 4. Then if we adjoin to G a new generator whose square is in G, then this group, you adjoin it and then you still mod out by order dividing 4s. That group is finite. Okay, so this is actually all the kind of gross parts of the theorem have been put in here, and so now we can prove. So from here the theorem is pretty easy. What's the theorem? So like I said, there's no like number or bound or whatever. I guess you can take. There is a bound here, but it's like some big tower. It doesn't really matter. The point is, the theorem is, this was proved by Sanov in 1940. Okay. BR4 is finite. Yeah, like I said, BR4 is less than, like, I guess, 4 to the 4 to the 4 to the 4. Or 4 to the 5 to the 5 to the 4 to the 5. Anyway, it doesn't matter. Why don't you, if you're really interested, you can figure it out and put it in the comments. Let's see. So for any group G, let G star equal G mod out by s to the 4 for all s in G. Okay, and so we prove the theorem by induction on R. Okay, so when R equals 1, there's one generator and it has order 4. The group is Z mod 4Z. Okay, and that's finite. It's very finite, there's 4 elements. Now, assume that BK4 is finite. Okay, by induction, the induction hypothesis. We want to add a new generator to the group, so we add a new generator to the group. Now, we really want to add a new generator whose square is in BK4, but we don't know that, right? So it seems like we're a little bit of, there's a little bit of a problem because we need the square to be in BK4 to apply the previous lemma. But it turns out that we can just, so we want to show that we can just do it in 2 steps. So we want to show that, want to show that bk plus 1, 4, which is equal to bk4 union g star is finite. And yeah, like I said, if g had g squared in bk4, then we'd be done, but we don't know that. So we only know that g to the 4 is equal to e. Okay, so g squared is equal to e. But e is in the original bk4. Okay, and so we can apply the lemma to g squared. So g prime equals bk, bk, let's write this again, bk4 union group generated by g squared star is finite. Okay, and now this is finite, and now we are allowed to do g to, we can take g, and now it squares in this group. Okay, so we apply the lemma again, and bk plus 1, 4, which is equal to g union g, so g prime union g star, which is equal to, of course, bk4 union g to begin with star, because this g squared is a subgroup of that, right? Is finite. Okay, so that's the proof of that. All right, so that's all we're going to prove in this video. But before, you know, I did tease at the start of the video that I would tell you the answer, that whether every BRn is finite. And so we're just going to talk about larger n. Okay, so in 1958, people showed that BR6 is finite of order 2 to the A, 3 to the B plus B choose 2 plus B choose 3, and we're A and B, where A is equal to 1 plus R minus 1 times 3 to the R plus R choose 2 plus R choose 3. These are R's. And B is equal to 1 plus R minus 1 to the R. And I said people showed this. Who showed this? Well, it seems like some other people did it for, there's something called the restricted Burnside problem. They showed that this is the size of the group corresponding to the restricted Burnside problem, but the person who showed that it's actually of this order for, you know, BR6 is actually Marshall Hall Jr., the guy who wrote the book that I have. He did that in 1958. He was so proud of it that he put it in his book, which I think came out in 1959. So he was like, it was on his mind. He was super excited about it. Okay, so this is Marshall Hall Jr. Okay, that's 1958. And actually, for n not equal to, or not in the set, say 1, 2, 3, 4. So these 1 is trivial, 2 we showed is abelian, 3 has an order that we figured out, 4 we showed is finite, but we don't know the order, or we didn't prove the order anyway. 6 is has that order. For n not in the set, it is unknown whether BRn is finite for all R. Okay? So you can get cracking if you really want to be famous. It turns out, though, that the question of whether Brn is finite for all n and r is no. Okay, and why is it no? Because in 1968, Adyan and Novikov showed that Brn, bad B, it's even worse now, is infinite if n is odd and n is greater than or equal to they have 4,381. And then in 1975, Novikov improved this to odd n greater than or equal to 665. Okay, same Novikov, I assume, unless maybe they were relatives. I'm pretty sure they're the same one. Okay, so yeah, so the answer is no, but there's still a lot we don't know about Burnside groups. For example, we don't know, like, for example, even 5, we don't know if Brn is finite for all r when n is 5. So there's a lot we still don't know about Burnside groups, but the general question of is it always finite is a no. And these papers are pretty complex, so far beyond the scope of this YouTube video. All right, so that's pretty much it. Yeah, as an exercise, why not prove the theorem for n equals 5 and write a paper about it? And that's a joke. But yeah, what's not a joke? You could from here figure out we've proved a bound for 4, right? And I said that it's some kind of tower. Where was the lemma? Yeah, this is not so hard. So figure out what the bound is for BR4 that we proved, because there's m to the n plus 1 over and over and over again. It's going to be some expression with a huge tower of exponents. Why not figure that out? There's a bit of nuance in there because we applied a lemma twice, but it shouldn't be so hard. And so go have fun with that. If not, yeah, I'll see you next time.